So today we're looking at optimization problems, which you've actually done in the past, starting with grade 10. We've taken a look at optimization problems with quadratics, finding that vertex, maximizing or minimizing with equations. So we're doing that today, but we're using the new tools that we've learned about in this course. But many of the problems are very much the same. So let's just take a quick read about this. So we are going to be using derivatives to solve our optimization problems. We'll be finding the best or optimal solution. So again, like maybe we want to minimize cost, maybe we want to maximize area. So in order to do that, we want to find those maximum and minimum values. Well, how do we do that? We find the derivative. We set it equal to 0, and that's going to give us the places where we have maximum and minimum values. So here's our general approach to solving these problems, and I want you to kind of just keep this in mind as you approach each problem. Again, I will give you a variety of problems to practice, and you'll probably come to school with some questions that you should touch base with me about, and I'll help you get through them because it's not just the same problems over and over again, right? So first step, read that problem carefully. I always highlight anything like units. I also like to draw a diagram. I start putting things together from the beginning in pencil, and then I erase and adjust as I go on. We want to introduce our variables, so stating those let statements, let x represent something, let y represent something else. We want to form an expression for the quantity to be minimized or maximized. So I'm looking at coming up with an expression where I can find maximum and minimum values of. I'm going to make an equation with one variable only. So usually we get given information to build an equation, something that has a left side and a right side. I find the domain of the function. So like maybe we have some restrictions on time or space. And then again, this is the kind of new piece that we're working with, is that we're differentiating that expression that we've made, setting it equal to 0 to find those critical numbers. We classify the critical point, so we have to show, is it a max or a min? And how do we show that? We use our interval table. And then, of course, we provide a conclusion, and that's nothing new to us. Make sure to include your proper units. So again, as we're going through it, sometimes we get answers that aren't reasonable, so you want to just make sure that you're looking at things, making sure that everything makes sense before you kind of pull it together and state your conclusion. So let's do an example together. So we have a farmer has 600 meters of fence. He wishes to enclose a field beside a straight section of a river of his property. Find the dimensions of the field so that the enclosed area is as large as possible. So we're maximizing area. Keep in mind that the fencing is required only on 3 sides. Okay, so a couple things here. First, I'm going to draw a picture. So here's my river, right? And here's where I'm going to have fencing. Sorry, it's not very square. I'm going to label this as X and this is Y. So I've got 3 sides of fence. So after I draw my diagram, I'm just going to do my let statements. I'm going to introduce those variables. You can use W and L if you want. It doesn't really matter. It's your choice. So I'm going to let X represent the width, and I'm going to let Y represent length. Okay, the next thing I'm going to write down is what I'm maximizing. So I want to maximize area. And I'm writing that down because essentially that's the expression that I want to use in order to like find my max and mins for. Okay, so I'm going to write area as equal to X times Y, you know, based on my diagram and my variables. So again, this will be my expression that I work with. Then I need to think about what equation I can build and use. So this is usually built with our known information. So some of the things that we know. So I know that there's 600 meters of fence. So ultimately I know that 2x plus 1y is equal to 600. So again, this is an equation. I have a left and I have a right. I'm going to use this equation just like we did in our previous classes, grade 10, grade 11, advanced functions. I'm going to use this equation to plug it into my expression. So I'm going to isolate y just because it's easier. It has a coefficient of 1. So I have 600 minus 2x. And then I'm going to sub that into my expression over here, okay, my area expression. So instead of y, I have 600 minus 2x, which I know is equal to negative 2x squared plus 600x. Now, a couple things to keep in mind here. And there are different ways to show that something is a maximum value, and we'll get into that in a minute. But I'm just going to quickly write down my domain. Okay, so I want to think about this a little bit. So when I think about x and y, I mean, really, it's greater than 0 because we won't have any area without 0. We know that. But, you know, ultimately, I'm going to start with this as something to think about. I'm not going to have negative values for length or width. Okay? All right. So this is what I'm going to work with. In grade 10, we we solved, right? Well, we didn't solve, but we found the vertex to find that maximum area. For us now, I'm going to move up here. I'm going to take that area equation. So a is equal to negative 2x squared plus 600x. And I'm going to find the derivative. Okay? And this is, I should put area as a function of x. So a prime of x is equal to negative 4x plus 600. So I want to know, basically, for my area function, right, I want to know where that maximum is happening. So I'm going to go ahead and set this equal to 0. So I get negative 600 is equal to negative 4x. So x is equal to 150. So this is my critical number. And so I now need to, so this is step 1, I now need to classify it and basically show that it's a maximum. So there's a couple different ways you can do this, okay? And I will accept any of these ways, as long as you classify it some way. So one way would be with an interval table, okay? Another way would be taking a look at the endpoints and this critical number, and comparing the y values and taking a look at those y values and showing, you know, the y value at 150 is higher than the endpoints, which in this case, we'd take a look at those zeros. Another way would be to describe or show the graph, right? Showing that this is a parabola, it opens down, so therefore it must be a maximum. Another way would be to take a look at the second derivative test. We didn't really go through this. I did refer this to you in our lesson the other day to take a look at in the textbook. So any of those ways, you can show that it's a maximum. So for me, just for this lesson, I'm going to set up that interval table to show that it's a maximum that way. So I'm going to take a look at x less than 150 and x greater than 150, and I'm going to take a look at that derivative function, negative 4x plus 600, and I know it's positive in this interval, negative in this interval, and so my derivative function is positive and negative, which means my function looks like this, and therefore we have a max at x equals 150, okay? So lastly, what I need to do is I need to come up with my y value. So I know y is equal to 600 minus 2 times 150, so y is equal to 300. Therefore, the dimensions that maximize area are 150 meters by 300 meters. So really, when I take a look at this question, there's nothing new from the questions we've done in the past. The new thing, other than how we solve, the new thing is using our derivative function, right, to find that x value, to find where we have a max or a min. The other thing I need you to show is classify in some way. So whether it's an interval table, that's what I did here, or comparing endpoints, or talking about the graph, or doing the second derivative test, any of those things will help. Will show, classify that something is a maximum. Other than that, everything's pretty much the same as what you did in grade 10. Okay, let's take a look at another type of question. And again, you'll have all types in your homework, so you're going to want to go over all of them. Here's our second example. We've got the sum of two non-negative integers, and that is 20. How should the numbers be chosen so that the sum of their squares is a maximum? What about a minimum? All right, so the sum of two non-negative integers is 20. So I'm just going to go ahead and write down that information that's given. And so instead of drawing a diagram, I'm writing that down. I've identified that I've got these two integers. I'm going to go ahead and do my let statements. I'm going to let x be one non-negative integer, and then I'm going to let y be the other non-negative integer. Okay, I'm going to write down that x is greater than or equal to 0, and so is y. So these are the things I'm thinking about. Now I want to think about, what am I maximizing? So the sum of their squares is a maximum. So I'm maximizing, and the last one was maximizing area. I'm maximizing the sum of squares. Okay, well, what does that look like? So the sum will equal x squared plus y squared. Okay, so this is my expression. So remember, we start with that expression. What are we maximizing or minimizing? I'm going to use an equation to sub into that expression. And my equation that was given is x plus y is equal to 20. I'm going to go ahead and rearrange for x this time. It doesn't matter. You can choose. And I'm going to use that to sub into my sum expression. So my sum, and this would be as a function of y now, is equal to negative y plus 20 squared plus y squared. I'm just going to go ahead and expand that out. So I get y squared minus 40y plus 400 plus y squared. So I get 2y squared minus 40y plus 400. Okay, great. So I'm maximizing this. So now what I'm going to do is take the derivative of this function. So I get 4y minus 40. All right, I want to find the values where I will have a maximum or minimum. So I'm going to set this equal to 0, and I'm going to solve. So y is equal to 10. So here is my critical number. I also know that x is greater than or equal to 0 and y is greater than or equal to 0. Okay? So I have x plus y is equal to 20. I know that x is equal to 20 minus y. I also know that therefore, since x has to be greater than or equal to 0, 20 minus y has to be greater than or equal to 0. So that means that 20 is greater than or equal to y. So now let's think about this for a minute. Y actually has to be in between these two values. Now, we also know this to be true is that if the sum of these two numbers is equal to 20, right? Obviously, y can't be something bigger than 20. The other way to write this would be like this. So y is any value between 0 and 20, including 0 and 20 with those square brackets. Okay, so now I'm going to classify to show that, like, if I have a maximum or minimum. Okay, so when I go to classify this, and remember, I gave you a list of ways we could classify. I'm going to start with that interval table again. So y less than 0, y greater than 0, and my derivative function is, what is it here, 4y minus 40. Okay, so it's negative here, it's positive here. That means that derivative function down, up, I have a minimum. Okay, so I have a minimum at when y is 20, we have a minimum, but we wanted a maximum. I want to know what values of y and x so that we have a maximum. So in this case, that maximum is not happening at our critical number. So I'm going to look at the endpoints. Well, the endpoints will be when y is 0, okay, because y has to be greater than or equal to 0. So actually, you know what we're going to do? We're going to write down, these would be our two endpoints, right? The two endpoints for y, and this is our critical number. Okay, so endpoint, endpoint, critical number. So I'm going to find those values. So this is 400. When I plug in the sum, when y is 0, right? When y is 0, that means x is 20. So our sum of the squares would be 400. When y is 10, our sum is 200, because that would mean x is also 10. Okay, so 10 squared plus 10 squared, 200. When y is 20, we also have 400. Okay, that would mean x is 0. So, therefore, for the sum of the squares to be a maximum, the integers are 0 and 20. Okay, now for a minimum, for the sum of squares to be a minimum, the integers are 10 and 10. All right. So that's it. Those are our two examples. You're going to face different problems in your homework. Again, think about using the derivative to find critical numbers. Okay, how am I going to classify? And then maybe also I do need to take a look at the intervals, or like basically the domain of whatever function that I create. In this case, it was the sum function. Okay, sum of the squares function. Okay, that's it. Good luck, and I hope you come to class with questions.